We'll come in on that day for review, and we'll take those problems, any ones, especially the ones that you have trouble with. We'll hammer those out and be sure that you know how to work those. And then if there's any time left, I'll ramble on about general topics and maybe give you something to work and see if you can do it. You know, the time won't be wasted. And then following that, we'll have an exam. And then after the exam, each time we'll jump into the next section. Okay. And with a class this size, I think I can get it done. As you finish the exam, turn it in, I'll grade it on the spot and hand it back to you before you leave. So you'll know what your grade is, which ones you missed, where you need to work, so you can get those firmly in mind for the final. Let's see. And then on the far right-hand side are the labs that we're going to be doing. So we'll have a lab next week, and then we'll skip a week. And we'll have a lab after that. I try to schedule the labs so that they occur on the days we have reviews. So that gives us plenty of time to get the review out of the way, do the lab, and we're not squished. Because sometimes when we go through introducing new material, it takes a little longer to get that out, especially if we have more than one chapter to deal with. And then the reports for each of the labs are due the next time we walk in to do another lab. So for instance, this introducing graphing techniques, that won't be due until the 14th of February. You can turn it in earlier if you want, that's fine. But it won't be due until we go in for laboratory techniques to do that. That's when they're due. Except for the last one. Since that's the last one, we don't have an indicator for that one. So that one is due actually the very next week. The molar mass of a volatile compound by the Dumas method, that report is due 1 week after we actually conduct the lab. By that time, you should be old hands at generating formal reports, and it ought to just come out like that. And that's another reason for having your lab notebook set up and done in some orderly fashion with all the information that you need to conduct the lab and all the results, so that you can take this and write the report from this. You don't need anything else, just this. You write the report from this. 6 months later, you can take this, go back in the lab, and repeat the experiment. I mean, you don't need the hard copy anymore if you do it right. Okay? Or anybody else that picks this up can go in and repeat your work. Okay? If you work for a company, you sign a contract at the beginning that everything you produce in the permanent lab notebook belongs to the company. If you don't sign that contract, oh, then you can walk out the door with it. Right? But usually, they pay for the research. They're gonna want to keep that notebook. Okay, so let's see what else of interest in here. Attendance. Well, attendance. The school says you can have excused attendance, and I guess that's for their funding process. You know, they need to show that the students are in class and attending and participating in order for the government to give them their share. So I have to report that. But since I'm not adding any points for attendance, it doesn't matter if you show up for the lecture. I record everything and I post it on Blackboard. So you can always have access to the lecture if you have to miss for illness or in the family, or if we have a snow day and it's not, if the school's not canceled and some of us make it here but you can't make it out of your holler, then you have access to the video. The only thing that you won't be able to do is the lab. So if there's a lab scheduled for that day and you miss it, then the only way you can complete your report is to lean on your lab partner and get the information from them so you can finish the report. And that's up to your lab partner. If you pair up with a stingy partner, then you may be in trouble. I've never had that happen before, though. Most lab partners are pretty generous because they know someday they may be in the same boat. So that's attendance. Bonus and extra credit. I handed out two things that I would identify as extra credit work for this one. And these are the only separate extra credits that I'm going to hand out for this semester. Okay. Oh, here we go. Okay, this one looks like this on the front. These are the instructions. And this is the work. It's an empty periodic table that you need to fill in using these instructions. Okay. This one, together with the second one, which is naming your compound. Here it is. 50 ways to name your compound. This is an extra credit. This one and that one together are worth half an exam. So you can rack up some points early on in case things get dicey toward the end. You've got some buffer. But you won't know, unless you've taken this course before, you won't know how to fill this one out until we get to that section. Hopefully we'll get to it today. We're going to do chapter 1 and 2 today. So if you're new to chemistry, then you need to lean on this one. I created this periodic chart because I couldn't find one that did everything I wanted it to. So I just went into Word, spent the time building. So this one has all the symbols on the periodic table. Every element now has a name and a symbol. There for a while we had a few that they had this systematic name that was kind of stupid. So we're not going to bother with that. But they all have names now, all the way up to 118. I got the symbols here, but I don't have the names, right? So to learn the symbols, you're going to have to look up the names. Okay. And the ones that you need to memorize are in the red boxes and the pink background. Okay, so it's about half of them. These are the important ones. Nearly all of them are in this upper part of the table. We have two down here for historical significance, right? U for uranium and PU for plutonium, right? Because we destroyed 2 Japanese cities with those. So if you've already got them memorized, or if you have a system that works for you for memorizing stuff, go with it. If you don't, you might want to invest in some 3x5 cards and make some flashcards. Right? Put the symbol on one side and name on the other. The act of making the flashcards is a memory exercise to begin with. And then you can master those symbols. Okay, let's see. There won't be any quizzes or tests in the lab section. I base it entirely on lab performance reports. Okay. And we only have those exams that are listed here. I generally don't give quizzes because it just takes too much class time. When I hand you back a graded, either a graded lab or a graded exam, if you think I've made a mistake, make yourself a note on the side, bring it to me, and let's look it over and see if I did make a mistake. Okay. Maybe I I transposed a key and put in the wrong answers. You know, that happens. Okay. Everybody knows to be considerate of your neighbor during exams. Everybody knows not to cheat. Okay. We won't have to hammer that problem. I generally, if somebody, if I suspect somebody of cheating, I generally don't take it to management. The next exam will be a whopper. I'll test everybody on the same material, right? But the suspected cheater will get one that'll knock your socks off. So I don't suspect we'll have that problem. Let's see. That's additional information that I have to put in there. Inclement weather. Everybody registered for inclement weather announcements with the school system. Okay, that's good. And the last thing I want you to do is print your name, sign it, and date it on that last sheet. Just tear that sheet off and turn it in. And put a number on there, a telephone number. Probably a cell phone number would be best that can receive texts. And the reason I want those is if I get delayed en route, say there's a traffic accident or I run off the road into a snowbank, I can contact everybody and let you know that I'm running late or that I won't even be here, which is highly unlikely, but it could happen. All right. That over there. Ooh, that's the wrong thing. Does any of this sound familiar? Oh, yeah. Okay. Oh, has everybody been into Blackboard to see if you can access the course? Okay. Know where to find everything? Okay. So we can dispense with that. If you, just a couple of things. As we accumulate grades, lab reports, and exams, then what I'll do is those will go into Blackboard also, so you can see them in your My Grades section. And then when I get enough of them together, like one exam and a lab report or two, then I can generate a running course average, and I'll put that in there also. And the heading for that one will change depending on the date that I put it in there. So I'll say course average as of such date. Then you know that that average is good up to that date. And if you turn something in after that date, even if it was due before that date, you turn it after, then you know that I haven't graded it yet and put it in there. Let's see, what else? I'll probably think of something as we go. So we probably ought to get into the course before we run out of time. There we go. Oops, wrong password. I forgot where I was. Here we go. Okay, so you don't need to see this. You do need to check your Southern email account once a day. Right. I'm not going to send you emails just willy-nilly. They'll be important. If you get an email from me, it'll be important stuff. And you may have noticed in Blackboard, on the left-hand side, there's a thing in there called SWBCTC email link. If you click on that, then you can send emails to anybody in the class without having to dig through the whole roster for the school. And you can send emails from there. You can't receive anything, but you can send them. And you need to go into your email account to actually get it. Unless you've linked your cell phone, you know, like I did, link your cell phone to your email account, and you'll always get it there. That's good. Okay, so let me shut this down and go to here, here. So, folder. And exam 1. Exam 1 will have chapter 1 and 2. So let's do this. You may have noticed in Blackboard that I've got the PowerPoints in there, but there are 2 other flavors. There's the PDF files, in case you don't have access to PowerPoint. By the way, everybody have Microsoft Office on your computers? Good. If you don't have it, then there's a link in Blackboard to Office 365 where you can get a free copy. All you need is a valid email, your valid email address from this institution, and they can identify you as able to download that free version. You can get a copy of it. Okay, I remember going with that. Oh, 3 flavors: PowerPoint, PDF, and I also have an HTML5, which is all of the PowerPoint slides, including embedded videos. If it has embedded videos and you call up the HTML5 version, it'll load up in your browser, and when you click through it, it'll show the videos too. PDFs don't do that, but HTML5 will. Okay, let's open these up and get down to business. Let's see, recommend content, yes. Last chapter 2, you don't need that one yet. Chapter 1. Let's see, 53 slides. Let's go kind of quick with this one. Can everybody see that? I've got a glare on that one. Let me see if this will help. Where's the glare coming from? I think the glare's. Oh, it's coming. Good. It must be auto adjust. Okay, be sure I'm recording. Yes. One other thing you may notice also is in the Blackboard, there are links in there to previous recordings. Right? So if you want to go in there and look at a recording that I made last spring semester for this course, they're in there also. And then you can go in after we've had the class, probably within 24 hours. I will have posted today's video in Blackboard so you can see them both. Because, you know, I may approach the subject a different way. Okay. Chapter 1. This is what my textbook looks like. But we're still going to talk about foundations. Chemistry, one definition, is the study of any substance and how it changes from one substance to another. And what we try to do is understand what we're actually seeing. If we see a change take place, we want to know, you know, is that due to pure physics? You know, in which case the substance didn't change really. Or is there a chemical change going on? And one way to understand that is to conceptualize the change on the microscopic level. We can see things that happen like color change or heat or cold as a consequence of a reaction, or maybe gas is generated, but that doesn't explain what's happening because you can't see what's actually going on at that level. So we develop theories and laws first, and then theories for explaining on the microscopic level what's going on the macroscopic level that you actually see and measure, as the case may be. So this is a good, it's good to start twisting your brain to think on the atomic level. You know, when you see some reaction that's going on, think of it in terms of, what are the atoms doing? All right, so matter is composed at the smallest level, composed of atoms, right? And the atoms for each of the elements on the table are different from each other. That's where we differ from the Greeks. The ancient Greeks had an idea about atoms, right? But they said every atom's the same. All atoms are alike. When Dalton came with his theory, he said, okay, yeah, atoms are the smallest part, but each atom of each element is different than the atoms of other elements. If you have two or more different atoms bound together, behaving as a single unit, we call that a molecule. Well, actually, if they're different, we call it a compound. If they're the same, they could still be a molecule. For instance, if we have two oxygen atoms tied together, or two hydrogen atoms tied together, they're diatomic molecules. But those are still elements, not compounds. The element only has one type of atom in it. Compounds have two or more. But they're still molecules, right? So the compound's a molecule, the diatomic or the triatomic or however many atoms bound together for an element is still an element, not a compound. So here's the way we write elements that behave in molecular form, like this. These are called diatomic elements. And on your know these chart, the one with the red boxes and the blue and so forth. The ones that are diatomic at room temperature and pressure are identified with blue boxes. Right? So you have hydrogen, and then you have these four in an inverted reverse L. So that one's diatomic. Nitrogen, oxygen, fluorine, bromine, iodine. Those right there, plus this one. Those are diatomic at room temperature. The reason that's important and the reason you need to memorize that and know that is if you come across a word problem that says we're going to react hydrogen gas with oxygen gas and make water. If you don't know that hydrogen is diatomic, oxygen is diatomic, when you write the reaction out as a formula, you get it wrong. If you write just H, just O, it'll be wrong. Okay, so those are diatomics, and those are the only diatomics on the periodic table. So a chemical reaction is written from left to right with the reactants on the left of the arrow and the products on the right. So in this case, we've got water molecule. Okay. In this case, they're saying two of them. So with the coefficient of 2, that means we have 2 of everything following it. Okay. And I think what's happening, okay, we're going to pass an electric current through there. So let's see, how do I write electricity? Voltage. So we're going to pass a direct current through there and split that molecule apart. And it's going to make hydrogen gas and oxygen gas. Okay. It's going to make one of these and 2 of those. Okay. So that would be showing a reaction as reactants and products. And notice we wrote these as diatomics. Now, if you turn that around, you can. I mean, the reaction can go the other way. If you have hydrogen gas and oxygen gas in a container, and you maybe put a little spark to it, they'll react violently, and the product will be water. And we use that to great advantage to launch our space shuttle into the low Earth orbit with this reaction going that way. This implies that the reaction is going to the right. But later on, we'll have reactions where we want to show that they can go both directions. So you just put the arrow the other direction too. Okay. Now, before about middle 17th century, what we consider as science today was investigated much like any other craft. You were proficient at doing something, and you acquired an apprentice and taught them how to do it until they got good enough at it, they go out on their own. But that's not good enough for advancing what we call science now. We needed a way to methodically extract information from what we considered chemical processes. And we developed a framework for gathering that information. It's fairly flexible as a framework, and depending on what type of information you're trying to get, the frame will change. But it's, for lack of a better term, it's a plan of action. Okay? In fact, it falls under the general heading of critical thinking. But scientific thinking is very specific to gathering a certain type of information. One thing that you do in a scientific investigation is you publish your work. You disseminate it to other scientists so they can learn from it. Right? There's no sense redoing. Or if you do redo, you're doing it to check to see if you can duplicate the work. If you can't, then the person who published that work needs to be contacted. Say, either I'm doing something wrong or you're full of baloney, right? And they will tell you to your face. You know, it's a ruthless business. It's very civil on the surface, but underneath, you know, there's extreme, intense competition among scientists, especially the young ones, because early on you got to make a name for yourself and get established, and then later on you can fritter away your time on stuff like the unified theory, which is what Einstein did for the remainder of his life. After he made his name for himself in his 20s, you know, he was established and he was free to putter away on stuff that really wasn't going to earn him any money. Okay, so we have this scientific method, we call it, for gathering information. And it basically breaks down into two general divisions. This upper one has to do with simply gaining information and answering simple questions. Right? So, and it usually starts with an observation. You see something that piques your interest, and you want to explain what's happening. So, after you've made the observation, you say, all right, here's what I think is happening. This is my hypothesis. I say, this happens because of this. Right? So you develop your hypothesis, and then you devise an experiment that's supposed to test to see if that hypothesis is correct. If it's correct, fine. Then you say, okay, now I know this much, I need to know more. And then you circle back around, make more observations, and just keep going like that. Generally speaking, what comes out of this section is a law. And a law is just an expression of what happens under certain circumstances, right? If I do this, I always get that. That would be a law. It doesn't explain why. It doesn't attempt to explain why. It's like Newton's first law, right? An object at rest tends to stay at rest. Object in motion tends to stay in motion. unless acted upon by an exterior force. It doesn't say why, it's just that's what happens. Or a second law. It says, if you apply a force to a given size mass, if you apply a force of this amount to that mass, it will accelerate at that rate. Doesn't say why, just that it happens. Now, what can happen is, after you've done several cycles here, you may start to develop an idea as to why, underlying microscopic reasons for something happening. So you may compile all of your results here into a theory, which usually involves creating a model too. I'll talk about a model in a minute. But that theory attempts to explain why something happens. Now, the advantage to a theory is that it has extreme predictive power. Right? With a theory that over time proves to be correct, you're able to more accurately predict things that are going to happen outside the realm that a law would cover. Right? So you can change conditions beyond the law's little basket and come out with reasonable results. But you also develop experiments to test this as well. You develop, they left out hypothesis, but it's in here. And we'll look at some theories as we go. So, you got this theory, and you use the theory to predict and then experiment, and then you compare it to what the theory says is going to happen. If the theory predicts something and the experiment comes out with different results, what are you going to do? You know, throw up your hands and go home? No, most scientists don't. There are three things that you can do if your theory misbehaves. You can modify it. That's the one that's given here. Modify your theory and then test it again with the modifications. Some theories are modified to within an inch of their lives. If it's just modified out into the stratosphere. Or you can restrict it. Restrict its use. So an example of that are Newton's theories. Right? So or Newton's laws. Actually, you can apply these to laws as well. You can restrict its use. So we know now that Newton's laws are only applicable within certain ranges of mass. Right? You get very, 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 very small, they fall apart. Subatomic level, you can't use Newton. If they get very, very big, you can't use them, like for black holes. Newton falls apart. So in those cases, you restrict its use and you go to a different theory. Right? For subatomic particles, you go to quantum theory. And for black holes, you go to relativity. And Einstein spent the rest of his life trying to unify all those theories into one. He never succeeded. Nobody has yet, actually. Your other option is discard, throw it out, and start over again. Sometimes you have to do that. It's hard on the ego, but if nobody is accepting your theories anymore, then you might as well throw it out and start over. I've got this, I put these little quotes on my door at my office, just to pique interest, see if anybody's paying attention. And the last one I put up said, science advances one funeral at a time. I didn't say that. I mean, I give credit to the author. What that's saying is, Scientists are human. You know, they treat these things like they're children. I don't want to throw my child out. So if my theory proves to be wrong and wrong and wrong and wrong, and I don't want to throw it out, it hangs around as long as I can. I've got my megaphone, especially for those scientists who have a really huge reputation. Their theories tend to hang on, even beyond their death. But the idea is that they have to die before you can advance. Okay, so I mentioned law. It's just what happens? What's the behavior? A hypothesis is simply an explanation for an observation. You're saying, I see this because of blah, blah. And a hypothesis, to be any kind of hypothesis, it has to be testable. You have to be able to test it. And just anybody in here has statistics. No. First rule of statistics is you can never prove a hypothesis. You can either disprove it, or you can say it's unlikely to be false. But you can never say absolutely that your hypothesis is true. And then theory is more often than not accompanied with a model. Now, model is just a representation of the small part of the universe that you're trying to describe. Think of battleship or airplane or some type of model. It's not the real thing, but it's a representation of the real thing. And the reason you need a model is because if you have the model and the theory that goes with it, then if you change something about that model, you want to know how it behaves, right? So if I have a model battleship and it floats along, maybe it's advanced, it's got a little motor it runs, then suppose I change something like I take out one of the plates below the water line. What's my model's going to sink, right? So that's predictable. Models can be physical in nature. You can make a model for a theory, and some models are like that. Like you think you know how the molecule is shaped. It's three-dimensional. That's your model for that molecule, and you can test how. Say it's an enzyme, and you have the substrate coming in here. Well, according to the lock and key mechanism, the substrate should fit into that, like a key into a lock, so that the reaction can take place. Or your model could be mathematical, and any type of equation will do as long as it satisfies the conditions of your theory. Measurements. Whenever we go into the laboratory, whether it's in a building or the laboratory outdoors, which is what I did for years. I was in agronomy, so we had field experiments. Right? Anytime you go to your chosen laboratory, you're going to make measurements. And every measurement is composed of a number and a unit. Okay, so this is the magnitude, and this is the scalar. What are your units? If I say, I am 6, what does that mean? I'm 6 feet. I have to put feet in there to make it 6 feet. Or if I'm 71. Not years, 71 inches. So I'm not quite 6 feet, 71 inches. So you got to have both, the magnitude and the unit, to make a measurement. These are just examples. This will be a direct measurement. If you measure the mass of something at 20 grams, then that's its mass. This one is a measurement that is a compound unit. Joule is a measure of energy, second is a unit of time. Usually when you make measurements, you don't come out with compound units. But if you use instrumentation that has built into it these calculations, then it might spit out the answer with compound units. That's possible. But it's perfectly valid to have joule seconds as a unit of measure. Or if you're measuring velocity, you might have m/h, miles per hour, or HR. Or in the metric system, maybe m/s, for meters per second. That's a valid measurement. It's compound. These are the fundamental units in the international system. Okay, mass is kilograms. Okay, so we have this platinum iridium cylinder in a double bell jar, inert atmosphere in some cave in France. That is exactly a kilogram. It's accepted as a kilogram. Okay? Nothing special about it. It's just that's what everybody agrees upon. This mass is 1 kilogram, and everything else is compared to that. The length, meter, used to be from the equator to the North Pole on the prime meridian that runs through England, and subdivided so many times, and that smallest subdivision was meter. Now we have another way of measuring, because we don't have to compare to the original. It's so many wavelengths of a laser beam produced by such and such a molecule. So if you have the instrumentation, you can generate a meter in your own lab. Time, seconds. That's a holdover from astronomical units. So we just try to refine it was already defined when the system was set up. So we just try to make it better. Temperature, Kelvin. Kelvin is an absolute value, which means that 0 on the Kelvin scale is absolutely no molecular activity at all. It's 0 degrees. The nice thing about Kelvin is the size of the unit. 1 Kelvin degree is exactly the same as 1 centigrade, Celsius degree. We'll get that later. Let's see. We might talk about amperes. Ampere is a measure of electric current. It's 1 coulomb passing in a conductor, passing a certain point for every second. So coulomb is the amount of charge per second is an ampere. Mole, we will use this one. Mole is an amount of a substance. For atoms and molecules, so many of them, right? 6.02 times 10 to the 23rd. Molecules or atoms is a mole. Okay? We're not going to use this one. Candela. Now, you take those fundamental units, and then a kilogram might be too large, right? So we may want to use something smaller. Well, as a matter of fact, the gram preceded the kilogram, but the gram is so small, right? So if you use that as your standard, if you miss it by just a little bit, the percentage difference is way off. So that's why they went to 1,000 times that as your standard. So the kilogram is one of those that already has the built-in prefix. Kilo means 1,000. So 1,000 grams is the standard. So 1,000th of that is the gram. Okay. But for everything else, like the meter, if you got, if you want to drive your car a long distance, in Europe anyway, you would drive it so many kilometers, 1,000 meters. Or if you had, let's see, what's another one? Time, seconds. Yeah, usually seconds don't vary that much, unless you're measuring something really short, right? Short time frame, like a millisecond. Small m is a milli, 1,000th of, or a millionth of a second. Micro, that's the Greek letter mu for micro. Well, these are big ones. Here's small. Here we go. Micro. 1 millionth of a second, 10 to the minus 6th. Nano, right? Everybody knows about nanotechnology, right? 10 to the minus 9th, or a billionth. Picos, 10 to the minus 12th. These are the main ones you need to know, right? Now, we use the term mass and weight interchangeably too often. Like an experiment or a lab exercise might be say, weigh such and such out to the nearest thousandth of a gram. What we really mean is determine the mass when we say weigh. Technically speaking, weight is a force and mass is an amount of substance. Mass never changes no matter where it is in the universe, whereas weight does. It's affected by gravity. It has a dependence upon mass, but it also has a dependence upon how big is the other mass, right? So that's why 60 pounds on Earth is only 10 pounds on the moon. Okay, uncertainty. This is one thing that trips many people up. I mean, even seasoned scientists. They know about it, but sometimes they ignore it. What's the uncertainty in your measurement? Anytime you make a measurement, there's going to be an amount of uncertainty. You don't know exactly what that measurement is. It may look like, 32 centimeters, but it could be 33, it could be 31. Maybe your device is off by a little bit, or maybe you read it instead of reading it right on. Maybe you had to slid over a little bit. You were looking at an angle, so you had a parallax effect that threw your measurement off. Just recognize that every time you make a measurement, there is uncertainty. So what we have to do is agree upon how to express the numbers in such a way that the uncertainty is implied in the number. Right? So if I make a measurement, it doesn't matter about the units right now. If I make a measurement like this, and I present that to another scientist, they automatically know these are the certain numbers. There's no doubt about those. This is the uncertain digit right there. I think that's what it is, but it may not be. So sometimes when you present a number, well, actually all the time when you present data in a publication, you have to say, what is the level of your uncertainty? That may be the uncertain digit, but you may say, that's good within 2 units maybe. Based on my data and repeated experiments, I think that this number is good within 2 units above or below. Okay? Then the question is, how do you do calculations with uncertainty? Well, before we do that, let's look at this example for reading. I don't know if I made the correction to this slide yet. So this is a burette. Okay? It's a special type of glassware that delivers an exact, as you can get, an exact volume of something from the burette into a container. Right? So you'll notice that it's numbered from the small numbers high to the large numbers low. That's because you're delivering a certain amount. So if you started at 0 and ended up here, you'd be almost 20 milliliters delivered. Okay? So you have to read it counterintuitively. So here we have, let's say, that's not even right, is it? There's 20, and here's 20. I just noticed that is not representative as a blow up of this picture. So let's stick to this one, okay? Let's just assume that's a blow up of this one. So how would we read this? Well, we're going this way, so it's past 20, but it's divided into 10 subunits, right? So 21 here is one whole unit, so these would be tenths. So this would be 20.1, and then the 0.1 to 0.2 is divided again. So you estimate what is that last one. The last one estimated, and for good reason, you estimate the one that has no line. This one's exact. This one is your estimate. And you could say it's like 0.15 or 0.14 or 0.13. It's up to you. That's what it is. In this case, we're saying it's 20.15. So this 5/100th position is our uncertainty. There's the certain, there's the uncertain. That's what it looks like for an actual measurement. And notice, with aqueous solutions in glassware, they always form this meniscus, this curve right here. And the glassware is calibrated to be measured at the bottom of that curve, right here. Okay. Now, what's the difference between accuracy and precision? There are two possibilities for accuracy. The rarer one is you have an idea, you know what the true value is. And then when you make a measurement, the difference between your measurement and the true value is a measure of the accuracy. Okay. More often than not, though, the true value is merely the accepted value for your community. But you're comparing your value to some accepted value. That's a measure of accuracy. Precision, you don't need to know what the true value is or the accepted value. Precision just says, how are your measurements grouped? So you got to make 2 or more measurements. Are they grouped very close together, or are they far apart? If they're far apart, your precision is poor. If they're very close together, precision is good. And in the popular literature, these are used interchangeably. Right? They'll say, how precise was that? When they really mean how accurate was it? When they say, that's an accurate measurement of blah, blah, blah. But it's really precision that they're talking about. So in the sciences, we have to be more careful than journalists, in quotes, or especially lawyers. When they get in the courtroom, all bets are off. Okay, so how do we deal with these? Let's see, wait a minute, I skipped something. Precision and accuracy. Okay, here's the dartboard representation of precision and accuracy. Right? If we have this one, I'm going to start on the right. We have the groups very close together, so it's very precise. And the true value, or the accepted value, is the bullseye. So I'd say it's both accurate and precise. For this one, it's reasonably precise, but it's terribly inaccurate. Okay? For this one, it's neither. They're not grouped together, and they're nowhere near the bullseye. There's another one that's left out, one that could be accurate, but not precise. So in that case, you would have darts like this that would be not precise because they're not grouped, but the average value of all those puts it right there. So it would be accurate, but not precise. And many a scientific paper has been published with that kind of data. And in the agricultural sciences, sometimes you don't have any choice because you're doing your experiments outdoors with environmental conditions that just go all over the place. And it's hard to get precise data. So what do? Well, you run the experiment over and over and over again, over years. So I had, actually, at the end, 4 years of field research data before I could publish it. Well, not publish it, present it to my PhD committee. It took that long. Okay. So how do we deal with uncertainty now? Well, first of all, we have to establish what are the significant numbers, or the significant digits in a number. How many are there? Okay. First rule, if your number has only non-zero integers, they're all significant. Right? This number has 4 significant figures. Okay. So then that begs the question, what do you do if there's zeros there? It depends on where the zero is. If the zero's to the left, all zeros to the left, leading zeros they call them, are not significant. Okay? It doesn't matter whether you have a decimal or not. Actually, you're going to have a decimal because nobody puts leading zeros on a non-decimal number. Right? I wouldn't say this number was 48. I wouldn't say 048. And it makes sense. So non-zeros to the left are not significant ever. Now, what about zeros in between, in the middle? If you've got a zero between 2 non-zeros, that one is always significant. It's a placeholder. If you don't have it there, if you don't have that zero there, then the rest of the number doesn't mean what it should, right? It should have this 7 out here in the hundredths place. If you don't have that zero, it shifts over to the 10th place, right? Then your number is completely wrong, right? So these are always significant if they're between 2 non-zeros. What about the right hand, 0 to the right? Well, it depends. If there's a decimal place in that number, an explicit decimal that's actually right there in the number, the ones to the right are significant. If there's no decimal, then that 0 is not significant. Okay? So if we have like our example there, yeah, that's not going to show up very well. We use the other side. Right? 150. 0 is not significant. We have 2 significant figures there. If we want to make that 0 significant, what do? Now it's significant. I mean, you don't want to do that just willy-nilly, but if it needs to be significant, then yeah, put the decimal in. So now that we've established significance, there's one other category. These are exact numbers. What I mean by exact numbers is they are numbers that have infinite significant digits. In other words, and it'll become obvious in a minute, when you use any exact number in a calculation, you don't have to worry about how many significant figures it has when you're trying to determine how many are in your answer. These exact numbers, they just don't enter in to the restriction of significant figures in your answer. And they'll always be conversion factors. Right? We'll talk about conversion factors in a minute. I better get a move on. We're still in chapter 1. Now, what's the difference between, actually, exponential notation and scientific notation are different. They're related, but exponential notation simply means that you converted a standard number into a number that has 10 to the exponent. Okay, that's all it's required. This number could be anything. A valid exponential notation for 300. For 300, exponential could be 30 times 10 to the first. You just move this over 1, store that 10s over here, and it's 30. That's exponential. Scientific is more restrictive. Scientific says this coefficient has to be between 1 and 10. So this is scientific. It's also exponential, but that's not scientific. This is. The advantage, you can take very large numbers, very small numbers, and make them manageable. There we go. Now, what do we do with significant figures? Now that we know how to do them, what value are they for calculating? We have two numbers here, and we multiply or divide. There are two rules. There's one for multiply, divide, and one for add, subtract. Multiply, divide is the simpler one. All you have to do is say, all right, multiply these together, I get a number. My calculator spits out a number. It doesn't know significant figures. You have to do that yourself. You take, if it's only multiply, divide in here, you find out which number has the fewest significant figures and apply that to your answer. Okay, and that means that you're going to have to know how to round. There are various types of rounding schemes. The one we're going to use is 5 or greater, you round up. Less than 5, you round down. What does that mean? That means you look, 1, 2. We need to round to that. So we look immediately to the right, no further. Is this one 5 or greater? Yep. That means this one goes up 1. Then you chop that off. Okay. Add, subtract. Add, subtract is a little different. For add, subtract, is it going to put that in? No. There should be a line right here. You line up the decimals, and then you add it together, and then you restrict your answer to the fewest number of decimal points. So even though we got this answer from that, we have to restrict it to only 2 decimal points. So we round this one to 8. Okay? Another possibility. What if you have 2 numbers that don't have decimal points in them? Or not implicit, right? Say we have 150 and 306. Okay? Well, if we bring it down, that, you don't have a decimal. Where are you going to go? Well, in this case, the decimal has to be explicit in order to use that rule. So there's no decimal here. That means we have to round it to those 2. So that means it's 4, 6, 0. 2 significant figures. Okay? All right. So, practical application. You're in the lab. You need to measure out a solution. This is not the best example, but let's just assume for the time being that you need to use 2 different graduated cylinders. And you want to measure out, let's see, what is this one? Is that the bottom of the meniscus? I'm not sure. what would that be? 1, 2, 3, 4, 5 divisions. So that'd be 2.2, 4, 6, 8, 2.9. Right, 2.9 milliliters. And you measure this one out as, you know, I bet they mean that to be 3. Because 3 is a true line, and 0 is our estimate. And then this one is 0.3. Right? And you add them together. Right? But this one is restricted. So it's 3.3 only for that. Let's see if it agrees. All right, it says 3.1. Why does it say 3? Because that's 0.3. Oh, it's only as accurate as the least accurate device. Did I do that wrong? Oh, I know what happened. I put in this 0 here. If I'd have left that out, then we would have had to actually say 3.0 rather than 3.1. I need to fix that slide. The point is, your measurement is only as good as your least accurate device. Okay, moving on. This is just an idea of problem solving. When it says when you approach a problem, what is my goal? That's basically for test taking techniques. What's the question? What's the problem asking? You know, you got to know what the question is. Can't possibly get the answer if you don't know what the question is. A friend of mine was a mechanical engineering student at LSU. He was a neighbor and a friend. And he said it amazed him at the number of students that would, as a consequence of doing a certain chapter in their book and then presented with a problem, would shoehorn the problem into what they had studied, right? Without thinking about whether it was the correct way to solve the problem. And they would come out with answers that were physically impossible. And of course, turn them in as the answer and get them wrong. So you need to know what the question is. And then you can ask yourself, how do you solve the problem? Right? What type of problem is it? Right? Is it a gas law problem? You know, is it a stoichiometry problem? I'll have to define that term later. And then devise a way to get there. Then you can work the problem. It's also a good idea to develop estimating ability. Right? When you've got a problem set up and you want to see, is my answer coming out right? I mean, if you believe your calculator, you put a lot of trust in those ones and zeros, then you're stuck. You just have to take its word for it. But if you're able to estimate the answer, then you can say, is this reasonable? First of all, is it mathematically reasonable? Or as an alternative, is it physically possible? If you do an experiment and you start off with 10 grams of this and 10 grams of that, and you come out with an answer, it wants to know how much product will be produced. It comes out with 5.87 kilograms of product. You're probably wrong. You just created matter. Okay, dimensional analysis is a fancy pair of words for keep track of your units, dimensions, you know, and this comes under the heading of unit conversions as one possibility, to convert from one unit to another. it's best that I just show you how to do it. So in this case, this golfer is 6.8 feet away, has a 6.8 foot putt. If it was me, I'd probably miss it. I don't play golf anymore, but when I was playing golf, that far away, I'll miss that one. Best I can do is just get close and then tap it in. So we want to convert that to how many inches is that, right? So if you start off with 6.8 feet, right, and you want to convert it to inches, you need something that will change those units into those units. Right? And the way you do it is you get an equivalency. How many inches are in a foot? 12 inches equals 1 foot. Okay? Now, how do we turn that into a conversion factor? Well, conversion factors are always equal to 1. They're unitary. How do I know that? Because just use simple math, algebra if you will. If I divide both sides by 12 inches, is that valid as an algebraic expression? If I do the same thing to both sides, I haven't changed it, right? That's valid. Okay? So I divide both sides by 12. So I get this one over here. And what's that one? That's equal to 1. So there's my conversion factor equal to 1. If I put 1 in here, that's true, but it doesn't give me my answer. It's just 1 times 6.8 feet is 6.8 feet. But if I substitute an equality, 1 equals 1 foot, well, actually, I should go the other direction. Let's do it this way. There you go. So now I can substitute for this one that conversion factor. There you go. Now, the thing about dimensional analysis is if you multiply two numbers, the units behave just like numbers. This one's in the numerator because all plain numbers like that, including their units, are divided by 1. So that means this is in the denominator, that one's in the numerator, they cancel. The units cancel. Then we divide 6.8 by 1, which is 6.8, multiply by 12, and we get, so I don't have to get my calculator out, 82 inches. That's dimensional analysis. Use your units to lead you through the conversion process. Now that was a single step conversion. You can chain them together, right? We happen to know this conversion factor, 12 inches equals 1 foot. Let's suppose we have a conversion that for which we only know certain conversion factors, and we don't know one that will do the whole thing in one calculation. Then you can chain them together as long as you cancel units as you go. Let me see, do I have an example here? Yeah. Suppose we want to go from pounds to grams. Suppose I don't know the conversion from pounds to grams. So happens I do know, but just for instance, say I don't know. I can get rid of pounds and go from the English units to metric. Okay, cancel that, cancel that. Now that calculation gives me kilograms, right? Let's see, is it going to cross them out? Yeah, kilograms. But now I want to go from kilograms to grams. So I need the conversion from kilograms to grams. 1,000 grams is 1 kilogram. So now the kilograms cancel, and we're left with grams. Okay? This is where you're starting, this is where you're ending. And then you fill in between with the conversion factors that will get you there. Then once you've got the units taken care of, the rest of it is math, right? So 4.5 times 1 times 1,000 divided by 2.2046 divided by 1 equals that number. Okay? So you practice that in your calculator, doing chain calculations. Algebraic calculators are a little more difficult than my RPN calculator. Reverse Polish notation is much friendlier to calculations than algebraics. But the companies that make algebraics, actually it's probably cheaper to produce those calculators. Plus they're better at marketing. It's kind of like, you probably don't remember this. Years ago, there were two forms of videotape. There was the VHS format for the big tapes like that. And then there were smaller ones called Betamax, made by Sony. Betamax was a far superior format, produced a better picture, better sound, but the proponents of VHS, I think JVC company pushed them. They were better at marketing. They took over the market with an inferior product. Of course, now they're both gone. DVDs took over, and then let's see what that advanced to. DVDs and then Blu-ray. Yeah, thank you. Blu-ray. They're going to have to go better than that now, aren't they? To keep up with the 8K screens. Blu-ray may not be big enough to hold that information. Let's see, what did I do? Okay. Okay. So let's talk about temperature. There are various ways of measuring temperature. Historically speaking, Fahrenheit was developed basically for living systems. So Herr Fahrenheit, when he developed the system, used living systems as to define the limits of his scale. Right? So 100 degrees for him was roughly body temperature. Okay? And 0 degrees was as the coldest that he could get. So he used salt, ice down salt, made 0 degrees. And then all he had to do was, once he found his 0 point and his 100 degree point, just subdivide it, right? So you get 100 units. Celsius was more interested in chemistry. So he developed his system with temperature that was, so the freezing point here would be like 32 Fahrenheit. Celsius, his 100 degree scale, actually was taller. No, here. 100, 0 to 100. This is the freezing point of water. That's the boiling point of water. Okay. You can produce that in any lab, anywhere. Calibrate your thermometers. So, the same physical process takes place at these temperatures. Oops, wrong. No, it should be 100 way up here. And 212 Fahrenheit. Okay, the same physical process happens, so the temperature is just a measurement. Right? It's arbitrary. So on this system, 0 to 100 is freezing point, boiling point. 32 to 212 is freezing point, boiling point. So you can compare those two and set up a conversion from one to the other. Right? The size of the degrees are different. The size of this degree is much smaller than the size of this degree. So you have to make that adjustment. And then you have to make the adjustment for the 0 position. Right? So the conversion then is from centigrade to Celsius is I always remember it this way. Fahrenheit equals 9/5 C plus 32. Your book is probably said 1.8, which is the same thing. But we're not really interested in Fahrenheit, you know, as a practical matter. But there might be a question on a test. Need to do it. Oh, by the way, these review documents, at the very back of the review document, there is useful information. Right, there'll be a page or 2 or 3 or 4. Useful information, right? Common polyatomic ions there. Periodic chart and formulas. Okay. If those pages are in the review document, they will reappear on an exam. So you just need to learn how to use that information. You don't have to memorize it. If you work enough of those problems, you'll memorize it automatically. But it'll be there on the exam. Kelvin. Okay, Kelvin is an absolute temperature scale. It was devised by Lord Kelvin when he noticed that on the centigrade scale and measuring volume versus temperature, that for gases, as the temperature increased, the volume increased. But physically speaking, it was only between these two. So he said, all right, what would happen if we just kept dropping the temperature? Just keep going. Theoretically speaking, it would go past through here, now here, and intersect at 0 volume, this point on the centigrade scale. And that turned out to be minus 273.15 degrees C. Okay? So he said, okay, Lord Kelvin's not good enough for me. I want a temperature scale named after me. So he said, we're going to start on my temperature scale. This is 0. So that means this 0 is 273 K. Doesn't have a degree mark in it, just K. Right? Then it just keeps going. So if you want to know what K is, you take the centigrade and add 273. 273 is good enough. We don't have to do 0.15. Okay? So that's a fairly easy conversion. Now, if the temperature is given in Fahrenheit and you need to do a calculation with gases, you're going to have to use K. So you got to convert Fahrenheit to C, then C to K. We're not going to spend time here because this is a comparison of the different scales. I'd like to see him get a normal mercury thermometer down to 0 K. I don't think it'll ever happen. In fact, we can never make it to 0 K. That's theoretical. Now, there's some laboratories that say, oh yeah, we've done it. Well, yeah, they might have done it for 1 molecule. They take a molecule that's coming at them like this, and they hit it with a laser, just the right energy, stops it. Technically, that's 0 K because there's no molecular motion. Okay, so this converts between scales. If you know one, you can get the rest, right? So if, let's see, this one is the one I was using earlier. Fahrenheit equals 9/5 C plus 32. If you know that one and you know this one, you're done. Because all you have to do to find, if you know Fahrenheit and you want to find C, you just rearrange the equation, right? Any equation in one unknown is solvable. You can always find out what that unknown is if it's only got one unknown. If there are 2 unknowns, then you need a value for one of them. Then you can solve it for the other one. Right? Otherwise, what do you do? If you've got 2 unknowns, what do you need? 2 equations. Right? 2 simultaneous equations and 2 unknowns you can solve. But if you only got 1 equation, you've got to have a number for one of those. variables before you can solve for the element. Okay, let's see. This is just a neat little calculation. Say, at what point is the magnitude of Celsius and Fahrenheit exactly the same? And this calculation says minus 40 degrees is the same for both of them. You know what minus 40 is? It's never gotten down what below like minus 15 around here. That's the lowest I've seen it. Like if you go to North Dakota maybe, or up into Canada in the winter, you might get 40 below. I have experienced 40 below. I used to work for a company, hotel and restaurant supply. They had a blast freezer. So they'd make hamburger patties, and then they put them in the blast freezer, freeze them quick, so it preserved the quality. But they'd also keep some of their product in there. And once a month, we had to inventory. So I was the new guy. So guess who got the inventory in the blast freezer? Okay. Other concepts. Density. Okay, now I want to introduce another idea. The capacity versus intensity. Some books will call this intensive versus extensive. I like capacity intensity better. The difference being that a measurement of intensity is the same no matter how much of the stuff you have. Right? So if you have, I don't know, water that's boiling. If you have a pot like this and it's boiling, it's going to be 100 degrees at 1 atmosphere pressure. If you have a pot like this and it's boiling, it's going to be 100 degrees too, no matter how much it is. So temperature is an intensity factor. Right? It doesn't matter how much you have. Most other types of measurements, if they're intensity factors, are going to be ratios, like something per something. Density is a good example of that, mass per unit volume. We'll encounter others along the way. Certain concentration values, same deal. And it's useful to understand whether you have a capacity or an intensity. If you're measuring the mass of something, that's a capacity factor because the mass will change depending on how much you have. Color. Right? You could have a lot of something. I could have this size shirt, or I could have this size shirt. It's still red. Okay, so sometimes it's written D equals NV, mass divided by volume. The thing about formulas like this is you can solve them for any unknown. Like we have 3 variables, density, mass, volume. If you know the mass and you know the volume, you can calculate the density. If you know the density and you know how much mass you have, you can find out what volume that represents. Just solve for volume. Right? And likewise, you can solve for mass. Okay. So let's see. Let's say practical example. Suppose you have a regular shaped object and you want to find out what the density is. What do I mean by regular shape? Say it's a cube, or it's a rectangular solid, or it's a sphere. Right? You can make physical measurements on those because we have a formula that will convert one measurement into the volume for that item. Okay, I think a sphere, if you know the radius of the sphere, it's 4/3 pi r cubed. Or if you know, if you have a cube, it's the length cubed. Or if you have a rectangular solid, you just need to know the length, width, and depth. Multiply them all three together to get the volume. Okay, that's the volume part. Then you just need to stick it on your balance and find out how much it weighs. What's the mass? Then you can do the calculation. But suppose you have an irregular object. How are you going to measure the volume of that? Well, if it's water soluble, you might be in trouble. If you put it in water to measure its displacement, then it'll dissolve before you make the measurement. Or, let's see, what else? If it's lighter than water, less dense than water, and it floats, you have to do something to submerge it, right? Because you've got to displace its volume completely. So when you put it in that amount of water, and you submerge your irregular object in here, the water's going to rise, and its volume is the difference between these two. Right? And then you just, the mass is easy. Get the mass, then you can calculate its density. But it's still an intensity factor. Okay, what forms of matter do we have? Solid, liquid, gas. Those are the only three we're concerned with. All right? We intuitively know what a solid is. But let's speak of it in terms of, in scientific terms. It has a definite shape. It holds its own shape. It doesn't need a container of any kind. And it has a definite volume. The volume doesn't change, as long as the temperature doesn't change. How about a liquid? Definite volume, yeah, not a definite shape. It assumes the shape of its container, but it doesn't change volume in the process. And then gases, they don't have a definite shape or a definite volume. So when you want to study a gas, you have to have a completely enclosed container. Okay, and this is what happens, right? A solid forms a rigid structure. The connection between the molecules is strong enough to hold them in that shape. If you add a little bit of energy, say you heat it up, like ice, the molecules start sliding past one another. And when that happens, they can't hold their shape anymore. But there's not enough energy to separate them completely apart. That only happens with gas. So you add enough energy to break all possible connections of any kind between these molecules, and you get your gas. Lots of space between the individual molecules. Okay. Now mixtures. Well, we should probably define first. Did I skip a slide? No, I didn't. A pure substance. What's a pure substance? Pure substance is something that cannot be divided by physical means into more than one substance. Right? You could separate it. You know, you should divide it like physically. You know, if you have let's pick something that, say you have a cake, right? And we're saying the cake is made out of just maybe one element or one compound. You cut it, all right? These two are the same substance. Keep cutting, cut. You get down to the point where you can't cut it anymore, but you haven't produced different substances. Every time you cut it, you get the same substance in each piece. That's a pure substance. Okay? It could be an element, like gold. 24 karat gold is a pure substance because there's nothing else in there but gold. Or it could be water, pure water, distilled water. There's nothing but H2O. Right? That's a pure substance. So pure substances can be either elements or compounds. You can't reduce them any further by physical means. Now, if you take two or more pure substances and mix them together, you could end up with one or the other, either a homogeneous mixture or a heterogeneous mixture. The difference is, a homogeneous mixture is, no matter where you sample your mixture, it's got the same composition of pure substances. So, my 14-karat gold ring has other base metals in it, usually maybe some silver, copper. But 14 divided by 24, what is that? 24 is pure, so 14 is 58%. Right? So this ring is 58% gold. No matter where I sample it, it's always going to be 58% gold. That's homogeneous mixture. Heterogeneous mixture is when you mix them together, they segregate. In other words, wherever you sample, you're going to get a different composition. From my experience, soils are just like that. Soils have different particle sizes everywhere you sample. So, examples of a homogeneous mixture, like I said, the alloy, salt water, sugar water, homogeneous mixture. They're all, and another name for homogeneous mixture is solution. The interesting thing is, when you mix two or more gases together, they always form homogeneous mixtures, every time. Does that seem strange? There's lots of space between gas molecules, plenty of space. Compared to the size of the gas molecule, the distance between them is infinite. There's lots of room for everybody. So when you mix gases together, they always mix in a solution, a gas solution, homogeneous mixture. Other things may not, like jelly beans, soil. Which one of these is homogeneous mixture? This brings up the idea of what's the question and how do you approach the answering of the question. Back to front sometimes is better. Look at what we're looking for, homogeneous mixture. Well, which one of these guys are mixtures? Pure water, that ain't a mixture. Copper metal, that's not a mixture. Right? Pure substance, both are pure substances. So it's got to be one of these. So now we go to this modifier, homogeneous. Which one's homogeneous? Well, I just told you, jar of jelly beans, that's heterogeneous. Right? Because every sample you take out is going to be a different collection of colors. Soils, I already told you that one. That's heterogeneous. So by process of elimination, gasoline's the only one. It is a homogeneous mixture of octane, which is a hydrocarbon, and other components, some volatile components, some additives to keep your injectors clean, things like that. Okay, what's a physical change? It's basically the change in the form of a substance without changing the nature of the substance, like boiling water, freezing water. You still have water, it's just a different form. Right? And if you have a mixture, this is like for pure substances, if you have a mixture, you can use physical changes to separate the mixture. Right? If it's based on particle size, all you need is a dry mixture and a sieve. You can separate. Or if you have a mixture, a homogeneous mixture of water and ethanol, you can distill it and get the ethanol out and sell it white lightning. Filtration. Chromatography is a little more advanced. It basically is, it separates based on the affinity of the components of your mixture with some stationary phase. Paper chromatography, you know, if you have your mixture and you place a dot on your piece of paper, you put it in your container with a little bit of liquid in the bottom, chosen correctly. Don't let the liquid come up to the dot yet. Make it wick its way up through the paper. And as it moves, the components of the dot that you place there move differently. Some associate more strongly with the paper, some less strongly. So the ones that associate less strongly with the paper tend to stay in the mobile phase, the liquid that's moving, and they move faster. So they'll be up here high. And then the ones that like paper better will be down here low. That's chromatography, an example of chromatography. Chemical change. A chemical change produces a different substance. It has different characteristics altogether. Right? Not just phase, not just what type of mixture is it. A chemical change produces different substances. So in a Bunsen burner, you've got methane gas primarily that's piped into your house or into the lab. Now, for a Bunsen burner, it'd be in the lab. Or your house would be in your stove, right, if you have gas at home. You might be burning methane. And when methane reacts with oxygen, methane disappears, oxygen disappears, and you end up with carbon dioxide and water as the products. Okay. Now, if you're using propane, you just substitute propane for this. It reacts with oxygen and also produces carbon dioxide and water, but in different ratios. But that's a chemical change. Let's see, we're getting short on time, so I'm going to have to skip this. Flow charts, sometimes they're helpful. If you want, you can use flow charts. That's chapter 1. It's already 3 o'clock. We got 2 hours left. And I might have to save some of this discussion for later. Yeah, we can save that one and that one. Safety code, we'll do that. Okay. This is the one we're going to do next week, I think. Graphing techniques. Yeah, okay, so I'm going to hand this one out. You can get a jump on this one. Graphing techniques. And should, since this is one that you don't need a formal report, yeah, this is one that has information to be included, and point value for each one is on the page, so you know how much it's worth. Much of this information can be gleaned from the pages prior to the questions. And then you have to draw some graphs. There's a bonus section. So everything up to the bonus section, which is on page 29, is required. And then the bonus is if you want to try to get some extra points. So with the bonus, you get points from bonus, and say you got everything right up to that point, and you get some bonus, then you could exceed 100%. You can bring this to class next week, since we're going to do this in class. You can just familiarize yourself with the material, have time to digest the introductory material, and then we'll talk about it in lab and do it in lab. But you can still take it home after that lab and bring it back the next time we go in the lab. Okay, does anybody need a short break? Good? You jump into chapter 2? Yeah. All right. I'll hand this other stuff out. The other stuff I have is more pertinent for formal lab reports. So you don't need those right now. If you're really curious, all this stuff is in Blackboard. You can look it up if you want. Let's see. So let's close this one and go to chapter 2. Where is it? Oh, it was hidden. Okay. So let me check this out again. Chapter 1 and 2. Yes, chapter 1 and 2 is for exam 1. So the next time we meet, we'll do review, chapter 1 and 2, and key off of that review document. All right. So, chapter 2. This is going to be a long recording. It's already 2 hours. We don't have to spend a lot of time on the history of chemistry. It's fascinating. I mean, the chemistry, you can trace it all the way back to the Greeks. They had their ideas about why things change from one substance to another. And all atoms were the same, but other influences change substances. Like what are the 4 basic elements? Earth, wind, fire, and water, I think. 4 basic. Then alchemy kind of took hold for quite a while. And it was more of a guild system. You know, you train somebody with your knowledge, you can tell anybody else. So there was no incentive to share. The first chemist was Robert Boyle. He's considered the first chemist because he performed quantitative experiments. He made actual numerical measurements during his experiments and related various variables by numbers. Now, as far as chemistry laws go, I've talked about physical laws with Newton. I know those fairly well. But laws, remember, the laws just say what happens and say why. So we usually develop laws first. And then once we get comfortable with the law, as long as it works right over and over and over again, then we can come up with a theory, perhaps, that explains why the law works and go from there. Well, Lavoisier, who was a Frenchman, came up with this law, conservation of mass, and it just says that you can't make or destroy mass in a chemical reaction. If you start out with so much mass of reactants, all reactants included, your products are going to be the same mass. And within the limits of our measuring capabilities, that's true. Then along came Proust. I think he was French also. Came out with a law of definite proportion. And what that says is, it doesn't matter where the compound comes from. Once you identify a compound and purify it, whatever its source is, the source is irrelevant at that point. From that point on, that compound will have exactly the same mass ratio of elements. Right? So water would be 18.2% hydrogen, I think. And the rest is oxygen. Whether it's derived from the space shuttle engine or whether you purified it by distillation. That's the law of definite proportion. Then the one that sometimes gets mixed up with that one is the law of multiple proportions. The law of multiple proportions was proposed by Dalton. And all it says is that if you have a series of compounds, say with 2 elements each, then the ratio of these masses increase by whole number digits. Right? So if you establish that you've got this much X, say you pick the size of your sample so that you have 1 gram each of these. Right? Then this one is going, whatever this one happens to be, Y grams of this one. This one's going to be 2 times it, and this one's going to be 3 times it. That's the law of multiple proportions. And you have to have a sequence of compounds with the same 2 elements involved. For instance, let's see, how about that work? That's acetylene, right? And then that's ethene, and this is ethane. Right? So you got the same amount of carbon, and each of these increases first by ×2, and then 2 more, 3 times. That's an illustration of the law of multiple proportions. So the law of definite proportions came first. Then Dalton came up with multiple proportions as an extension. Okay. Dalton, at the beginning of the 19th century, accumulated all the information that he had and all the information that he could glean from other scientists' work that he trusted. And he put together an idea of how these things were actually working. Why did these things work the way they do? Okay, now we've got a theory. Well, he started with the basics, right? Like the ancient Greeks is each element is made up of tiny particles called atoms. That's the simplest particle of each element. Then he said the atoms of this element are different than the atoms of that element. That's where he diverged from the ancient Greeks. The atoms of one element are different than the atoms of another element. He didn't know how. You know, we didn't know, at this time we didn't know about subatomic particles, or at least it wasn't disseminated well enough for him to incorporate it into his theory. But he did know that in some fundamental way, these individual atoms were different, and that's what made each element different. Then he said that chemical compounds are formed by combinations of 2 or more of these different elements. And the ratio is based upon the number of atoms, not on the mass. Up to that point, all they knew was mass ratio. Now he's given them a reason for the masses being different. Is that the ratio is based upon the number of atoms in each molecule of each element. And he said during the chemical reaction, this is why Lavoisier's law, conservation of mass, works. Because in a chemical reaction, you just rearrange the atoms. Right? You don't create any, you don't destroy any, you just shuffle them around. And the products come out with a different arrangement. They give your products different properties too, based upon the arrangements. But the atoms are not destroyed, they're not created, they're just rearranged. Okay, that was Dalton. Let's see. Gay-Lussac did work before Avogadro. Avogadro's work was based upon Gay-Lussac, but Avogadro took it further. Gay-Lussac, probably Frenchman, measured the volumes of gases that came out of reactions. And he changed conditions, temperature and pressure, and saw what consequence there was from that reaction. Avogadro then took this work and hypothesized, which was borne out later, that for gases, we'll find out when we talk about gases later, I'll give you this again. But to define a gas, you need 4 values, physical values: temperature, pressure, volume, and how much of it is there. N is the abbreviation for moles. How much gas is there? So you know these 4, you can define the gas and its behavior. You can't actually define the chemistry of it, but you can define its behavior. So what Avogadro said was, if you have 2 containers, right? I didn't draw them exactly right, but if the volume of this one is equal to the volume of that one, and the pressure inside is equal to the pressure in each one, and the temperatures are the same. If all those 3 factors are the same, then each container holds exactly the same amount of gas. Okay, that's Avogadro's hypothesis. And what that did was that opened the floodgates for chemistry in the early 19th century. Up to that point, chemists only knew mass. Right? They couldn't relate. I mean, Dalton's theory was out there, but they couldn't apply it to their reactions. So university professors and their graduate students that were doing experiments were just lost. When something went wrong, their reaction didn't work, they couldn't figure it out. That was a tragedy. But companies were depending on their chemists to keep their reactions going in the most productive fashion. And when they went wrong, they couldn't figure it out. Those companies lost money, and lots of it. So they got together in 1865, I think, in a place called Karlsruhe, Austria. There's a university there. So they all got together from all over Europe and said, we're going to put our heads together and figure this thing out. Why are our reactions going cuckoo and we can't figure it out? So they were there for 4 or 5 days, having meetings, eating and drinking. Probably a lot of beer in let's see, where was that? Austria. Okay, yeah. Or maybe it was in Bavaria. No, it was Austria. Excuse me. Anyway, they came out of there all scratching their heads. They couldn't figure it out. Well, as it turns out, there was I don't know if he was a student of Avogadro, but he was certainly using Avogadro's laws, his hypothesis, to work with chemical reactions. And he had published a paper. His name was Cannizzaro, in Italian. And he was out there. He was kind of low down on the totem pole, as far as prestige goes. So he just waited outside the meeting, and he was handing out reprints of his publication. And he gave credit to Avogadro for his work. And they, the people that were taking his reprints, they were gracious when they did it. They took his reprints away, and they went back to their respective companies and universities, and some of them read the paper. And light bulbs started going on all over Europe. Said, that solves everything. Now we know that how to determine how many molecules are in this one versus that one, and how the ratios work. All right, so they started with gases. They did their reactions with gases. And this relationship was telling them what was actually happening at the atomic level in their reactions. Now they could figure out they didn't need mass anymore. I mean, mass, they used mass. But this extra bit of information started solving their problems. And that's when chemical industry in Europe really took off, once they figured out those problems. Okay. Wrong hand. Okay. So what Gay-Lussac was saying, and Avogadro picked up on, was if you have 2 volumes of hydrogen and 1 volume of oxygen, you get 2 volumes of water in the gas phase. So this gives you a reaction ratio, like 1 volume there, 2 volumes there. And what does that mean in terms of reaction? Well, we've already seen the reaction, the way it was written, I think. Hydrogen gas plus oxygen gas yields water, and in this case, gas. So to balance this equation, I need 2 here and 2 here. So what does that say? 2 volumes of hydrogen, 1 volume of oxygen, 2 volumes of water. That's what Gay-Lussac said. And Avogadro picked up on it and said, oh, it's even deeper than that. You know, and he elaborated. 1 volume of hydrogen and 1 volume of chlorine makes 2 volumes of hydrogen chloride. So these ratios were giving you a clue for at least gas reactions of what these coefficients are. Okay, that's a graphical representation of this equation. Okay. So we need to know, we need more information. If we want to know how and why chemical reactions occur, we need more information about the individual atoms. Right? All Dalton could tell us was that they were elementary particles. I mean, that's it. They're different in some way, but I don't know why. So along came J.J. Thompson. He was an Englishman. And he started by postulating a sub-elementary particle that was present in every atom of every element. A negative charge. And he actually determined the charge to mass ratio of the electron. And how is it related to, say, the other elements? Like he said, okay, it's about 1,800 or so times less massive than the hydrogen atom. Okay. And he used a cathode ray tube. That was big in those days. You know, they were fascinated with electricity, and especially in societies. And they would have these static electricity generators. You crank up, fill up a charge, and then you get a line of guests together, all dressed up in their wigs and finery, and everybody hold hands, and then the one person on the end would touch the charge, and it'd go through everybody, and they'd all jump. You know, have a big time. But scientists were actually using it to do research and found that the nature of the electron, as it came to be called, was negative because we had established at that point the bipolar nature of matter. You know, you could build up an electric charge of either positive or negative nature. And you could either bend it with electrostatic plates, or you could bend it with a magnet. you know, and if it was positive, it's bent one way, if it's negative, bent the other way. So Thompson postulated that this element, or this elementary particle, was negative. Well, Millikan wasn't satisfied with that. That's generally the way it goes with science. Say, somebody's answered a question, the answer generates 10 other questions. Right? So he said, I want to know, you know, just what the mass of that particle is. So he used some mathematical calculations and devised experiments to measure the mass of the electron. And he did it. He repeated the experiment thousands of times, literally. Every spare moment he had when he didn't have teaching duties or didn't have to manage graduate students or whatever, he was doing this experiment on his own. And he determined that the mass of the electron was very small, 10 to the minus 31 kilograms. Tiny.
A thin mist of oil drops is sprayed into the top chamber. Oil drops acquire a charge from air molecules ionized.
That's a little. Let's see if I can turn that down. That's good. Let's go back. Start it over.
Mist of oil drops is sprayed into the top chamber. Oil drops acquire a charge from air molecules ionized by an X-ray source. When the voltage on the charged plates is adjusted properly, the drop can be suspended between the plates. Several measurements allow determination of the charge of a single electron.
Okay, so that's a schematic version of his oil drop experiment. But the oil drops are very small, so he needed a telescope to see into the evacuated chamber. You know, and he used oil because it had very low vapor pressure. So in that evacuated chamber, they said acquired from air molecules. Actually, you know, maybe there were some air molecules in there because, you know, we can't create a perfect vacuum. But it was evacuated, and he could see through a glass with his telescope, and he could watch the drop and adjust the voltage. And by calculating what the voltage was, he could tell what the charge was. So he did this experiment over and over and over again, and some of them required more voltage, some of them required less voltage, and he found that the voltage differences were varied by a whole number of units. Right? So he worked his way down to the very smallest one, and then he said, that's the one that has one electron. I got to retake control. There we go. Now, Henri Becquerel, Frenchman, was working with radioactivity. A lot of people were at this time. The Curies were, Marie and her husband, working with radioactivity. They didn't understand how dangerous it was at that time. In fact, it eventually killed both of them. But before they did, they discovered these things, and they found that radiation comes in 3 flavors. At that time, it did. There are other versions of radiation now, not the kind on Star Trek. That's theta radiation. It's that. I don't know. You can take a shot and be immunized. That's kind of stretching it. But the radiation they were concerned with came in 3 flavors. They knew that gamma radiation, there was absolutely no mass involved. This was purely light. High energy light, gamma radiation. Right? Beta particles turned out to be very fast electrons. But it's just the difference is the source of the electron. The electron comes from a radioactive nucleus. It comes from the nucleus of an atom that's undergoing decay. Alpha particles, these are negatively charged, of course. Alpha particles are positively charged. they're, by comparison, very, very heavy. It's basically the nucleus of a helium atom. So it's got 2 protons and 2 neutrons. I'll have to define that later. But it's very heavy, and it has a 2+ charge. Right? So you got your negative matter, you got your positive matter, and light. And those are basically the 3 types of radiation that were known at the time. So along comes Rutherford, Ernst Rutherford, who was an Englishman. And he postulated that there were various theories floating around. And one of them that was common, by this time they knew that the atom, the neutral atom, of course, had a mixture of positive and negative charges. And they were equal. That the same number of positives as negatives, that's why it was neutral. So one model said that they're all scattered in there together in the atom, like we call it the plum pudding model. But Rutherford said, nah, I think that the positive charges, which is most of the mass, by this time we knew about protons. Right? We knew they were very massive compared to the electron. He says the electrons are out here somewhere, outside the nucleus. So it had a very, very, very dense nucleus with protons in it. And then the electrons were out here. So he devised an experiment to compare and say, all right, they both can't be right. So he did what we know now as the gold foil experiment. Let's see, we have a no, we don't. Okay, I'll describe it to you. Back up, back. There. So he devised the gold foil experiment. He said, he used gold foil because he knew it could be hammered very thin, just a few atoms thick, and it would still hold together. So he put this gold foil right here, and he surrounded it with detectors, probably photographic film. Right? So he had these detectors spaced around here. He said, what I'm going to do is I'm going to fire a very dense particle at this gold foil. And he knew that the alpha particle was very dense. So he had this source in this lead container of radioactive material, and he fired alpha particles at it. Now, to make sure that it went straight, he used a collimator. So what you do is you have a slit there, or a very fine pinhole, and then you have another one lined up here, like that. So only the ones that are going straight are going to make it through both of them. So they're going straight. When they strike the atoms here, if it's a plum pudding model, everything's going to end up right here, right? Because the density throughout is the same. Right? It's just going to go straight through. It might hit some, but it won't matter. The density is so low, they're all going to end up over here. Okay? If the plum pudding model is correct. If his model, if the nuclear atom model is correct, then what you're going to get is occasionally, well, most of them are going to end up over here because it's all empty space, right? Except for that dense nucleus. If it strikes the nucleus, a glancing blow, you're going to get some over here, or here, or maybe some back here. And occasionally you get one that strikes dead on and it goes straight back. Most of them ended up over here because it's mostly empty space. But occasionally you got a ping over here, 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 here. That proved that his model is correct, the nuclear atom. So the densest part is in this nucleus and the electrons are out here. Okay, so now we're building a model of the atom that we can use to help us explain why atoms react the way they do, why elements react the way they do. Okay, so now we've identified electrons, protons. The problem is we can't account for all the mass of every element with just protons, which is where electrons, you can discount them. They don't worth anything. So we can't add any charge because if we do, we've got to add electrons. And then we can't do that. So it was postulated we need a neutral particle that's as dense as the proton, but not charged. So we created neutrons to fill that gap. And that satisfied the progression of elements as they get heavier and heavier. Okay, so the nucleus of the atom is very dense. That's where the protons and neutrons reside. And our abbreviations for them, we say E plus for protons, say E minus for electrons, and N0 for neutrons. So if it has that 0 there, you know it's a neutron. If it doesn't, you know it means moles. Okay. There's so many elements in the alphabet, so we have to make do with what we have. Okay. And the nucleus occupies such a small part of the atom here compared to the rest of the atom that's occupied by electrons. Now, concept of isotopes. Now that we know that neutrons are available, we also know that when we isolate an element and characterize it, every atom has exactly the same protons. In other words, if you have a certain number of protons, you know you have that element. So if we have, if we have 8 protons, we've got oxygen every time. If you change that number to 9 or 7 or whatever, you got a different element. But we also noticed that some portion, once separated, we count the atoms, and technology is here to do that. We count the atoms. Some of them weigh 16. Right? If you have 8 protons, that's the atomic number, and 16 is the mass number. And say we don't have a charge, right? And there's only one of them, so we don't put anything there. So if you have 8 protons and 16 minus 8 neutrons, so you have 8 protons and 8 neutrons, you have oxygen for sure, but you have an isotope of oxygen that has a mass number of 16. Occasionally, you might have an extra neutron. So if you have an extra neutron, there, now you have 8 protons and 9 neutrons. Chemically, they behave exactly alike. But one is heavier than the other. Now, why do they behave alike chemically? When 2 atoms approach one another, what do they see first? Electrons. They see electrons, right, as they get closer. So the electron interaction is where the chemistry happens. Okay? So this oxygen, since it has 8 protons, if it's a neutral atom, it'll have 8 electrons out here. This one has 8 electrons out there too. So chemically, they behave the same. Okay, those are isotopes. Now, naturally isolated sample of oxygen, or any element for that matter, will have a mixture of isotopes. Most of them will have one isotope that dominates, and the rest of them will be minor components. Some of them may even be radioactive. So they're in the process of changing from this element to some other element. But many of them are stable. Here's sodium, for example. This one on the right has an extra neutron. Has 11 protons. And the reason I drew it that way, around a symbol, you have 4 positions that are identified and reserved for information. This is the information for protons. This is the information for mass number. This is for charge. And this is for number of atoms. Okay. If you only got one, you don't need that one. If you're not interested in the charge, you can throw that out. If you're not talking about anything nuclear, just a chemical reaction, then you don't need those either. Because if you have a symbol, it's automatically, you know how many protons there are. But if we're describing isotopes, we need to use that convention. Okay, there you go. Okay. If X contains 23 protons and 28 neutrons, what element is it? Okay. Just look at the table. I'm going to use this one so it's closer for my old eyes. And they're arranged from upper left to lower right, getting heavier and more protons as you go. So left to right, you'll add a proton each time you go from one square to the next. So all you have to do is follow along. 19, 20, 21, 22, 23. These numbers here are the atomic numbers, the number of protons. So 23 is vanadium. Okay? So that's vanadium. And if it has 23 protons and 28 neutrons, what's the mass number? So 23 would be here, and the mass number is 51, right? Let's add those two together. All right. Now, when reactions occur, certain types of attractions are involved. Right? One type of attraction is called the covalent bond. The covalent bond is one in which electrons are shared between elements, as opposed to ionic bond, in which electrons are transferred completely from one atom to the next. When that happens, all you have holding them together is electrostatic charge. So if we have sodium and chlorine to make sodium chloride, an electron is transferred from here to here, makes this one positive and that one's negative. Right? And how do you know that? Because if sodium has 11 protons, it had 11 electrons, now it has 10 electrons. So the difference in charge is a +1. Right? The balance of negative and a positive. It's a +1. But chlorine starts out with 17, and now it has 18 electrons. So its balance is toward one extra negative. Right? So once that happens, you get an electrostatic charge. One likes attract, right? Positive, negative. That's an ionic bond. For things like water, where you're combining hydrogen and oxygen, and that's not balanced. But you don't transfer electrons completely from one to the other. You just share them. And we'll talk about why that is, why that works. But that's the covalent bond. And counterintuitively, these bonds are stronger than those bonds. Covalent bonds are much stronger than ionic bonds. Okay.
Halogen atoms will combine to form single bonds. Atoms combine to share electrons, forming a covalent bond. The covalent bond is often shown as a link between atoms, although it is actually a sharing of electrons. The diatomic chlorine molecules maintain their bonds even if they collide with other molecules.
And remember, the chlorine at room temperature and pressure is a diatomic molecule. It's one of those right there. So chlorine gas is going to be Cl2. Here's your ionic bonds. And we have special names. Of course, a charged atom is an ion. But if it's a positive charge, we call it a cation. If it's a negative charge, we call it an anion. Just memorize it. I could make an argument for why they're called that, but I think it's simpler just to say if it gains an electron beyond its neutral state, it's going to go negative, an anion. If it loses, it's going to go cation. And it doesn't have to be just a single charge. It doesn't have to be +1 or +2. It could be -1, -2, -3. It could be +2, +3, +4 charge. And it all based upon the difference in how many protons, how many electrons. Now, you can never create an ion by changing the number of protons. What happens if you change the number of protons? You got a different element. Yeah. So you have to do all this charge thing with electrons only.
Water, on the left, is a molecular substance that exists as a liquid at room temperature. Sodium chloride, on the right, is an ionic substance that forms solid crystals at room temperature. Molecular water has covalent bonds, holding hydrogen atoms to oxygen atoms. But there are no bonds between molecules, so they move freely in the liquid. The ions in sodium chloride are held together by ionic bonds, which restrict motion of ions in the solid crystal.
Okay. So the point of this is that covalent bonds produce molecular substances. And the covalent bond holds that molecule together. It behaves as a single unit. Whereas ionic substances, you've got positives and negatives attracting one another. And they, physically speaking, they behave independently. But when we represent them in a formula, that's not the physics of it. The physics of it is a matrix of positives and negatives. All the negatives would be surrounded by positives, all the positives surrounded by negatives, and they form a crystal lattice. This is a simplest whole number ratio of sodium and chlorine in that crystal lattice. Okay? It's not really a molecule. I just want you to understand that. You still got those charges. We just don't write them. How do you know if it's that and not a molecular substance? Rule of thumb, if the cation comes from this side, the anion comes from that side, you've got an ionic substance. The farther apart they are, the more ionic the character of the bonds. Okay? So if you have two elements that are from similar parts, then that usually means from this side. If you get two of these reacting, you're going to get covalent bonds in molecular substances, including hydrogen. We stick hydrogen over here just for balance. Hydrogen's kind of an animal of its own. It doesn't fit anywhere. But if you have two of these together, What you get there is a special kind of bond that we're not going to spend a lot of time on. It's called a metallic bond. And there are various theories as to why that works. But these are not covalent bonds between metallics. And the reason I say that the way I do is that the periodic table is divided in gross manner between the right of this pointer as I go down like that. Over here is non-metals, over here is metals. So most of the elements are metals. Okay, so if you have an isotope of this element, let's say, and it's charged, okay? It has 54 electrons and 78 neutrons. What's the mass number? The mass number is going to be the number of protons plus neutrons. So you've got to find out how many protons this represents. Can we do it from that information? Yep. You know the number of electrons, but you know that it's got a positive charge. So the number of protons has to exceed the number of electrons by 1, doesn't it? So we have 55 protons. And then 55 plus 78 is 133. So the mass number should be 133. By the way, what element is that? 55? Let's see. Cesium. Yeah, cesium. This is kind of a tricky question. Which of the following statements regarding Dalton's atomic theory are still believed to be true? Elements are made of tiny particles called atoms. Yeah, that's still true. All atoms of a given element are identical. Not anymore. Not with isotopes. They're chemically identical, but they're not identical. If that makes any sense. A given element always has the same relative number and types of atoms. Same relative numbers. Oh, a compound always has the same relative number and types of atoms. That's true. That's what makes it that particular compound. Atoms are indestructible. Yeah, we know better now. With radioactivity. Right? So those two are still basically true. Now, the periodic table, how is it divided? I showed you metals and nonmetals, right? So if you can see that red line right there, when you fill out your extra credit periodic table, you'll need to draw that line in there. It's also divided into groups or families, right? So groups are vertical. So here's one group, here's another group, here's a 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 group. These, some of them have names, right? The noble gases, of course, right here. These are halogens, right? So let's see, a lot of cars use LED lights now, but there for a time, halogen bulbs were big. And I think they had iodine in them. And then these are the chalcogens, named for combinations with oxygen. These are the pnictogens, starts with a P, P silent, P-N-I-C-T, pnictogen. Then over here we have the alkaline metals and the alkaline earths, or the alkaline earth metals, sometimes they're called. Then this group right here in the middle transition from one side to the other, so they're called transition elements. And then down here we have the lanthanides, based on the first element in the group, lanthanum, and it's extracted from this place right here and brought out here. The reason for that is, if you stuck it in there where it's supposed to be, the periodic table will be huge. So we just pull it out here, along with the actinides. So actinium is here, and then everything behind it, when you get to the end there, and you can go back to this one, 103 to 104, and continue. Periods. The periods go from left to right. They're horizontal. Okay? And the reason they're called periods, let's see, has anybody had physics? Have you ever heard of something called periodic motion? Periodic motion is motion in a physical sense, but it's motion in which the object goes someplace and comes back. So it goes through a period of time, it goes out here and it comes back to here. It starts all over again. So the period here is it goes down to one end and it has to start all over again. So it goes down to here and starts over again. And it goes down here, it's got to start all over again. That's a period. A good example of periodic motion is the pendulum. It moves, but it comes back to the same spot each time. Same spot. Okay. Okay, so here's the division between metals and non-metals. We've got names here. It doesn't name these right here. The carbon family, the boron family, they don't have special names. Now, in reactions, when you find an element in a compound, if it comes from the alkali metals, this first group, it's going to have a +1 charge. And you can see up here in the upper right-hand corner the charge that's assigned to it. The alkaline earths have a +2 charge. Okay? It's important to know that when we start naming compounds and writing compounds so that you know how the charge is balanced. Oh, it's on this page too. Then you skip over these because for the reason will become obvious later. Skip over here, these are +3, +3, +3, +3, +3, at least for those. Okay. Then that's the alkali metals. Halogens are -1. When they're combined in an ionic compound, they're always -1. Right. The reason they have other charges in here are not necessarily because those are charges. They're referencing something else called oxidation state. We'll have to talk about that later. So for our purposes, these are all -1. These are -2. These are -3. Carbon can go either way. It's kind of halfway in between. It can go +4, -4, or in between. It depends on what it's combined with. Okay. Naming compounds. We're going to start with binary compounds for naming purposes. Just to differentiate between the types of compounds, or among the type of compounds. If you have 2 elements or 2 components with opposite charges, you have a binary compound. The reason I say it that way is it's obvious that this is a binary, right? But sometimes you have polyatomic ions that behave as a single unit. So you could combine sodium with carbonate. This behaves as a single unit, that. So this becomes a binary compound. That against that. Sodium still has a +1 charge, but carbonate has a 2- charge. Okay? So that means in order to balance it and make it neutral, you need 2 of these, right? 2 times +1 is +2, balances the 2-. Okay. Binary ionics. Typically, a metal and a non-metal will make a binary ionic. And the farther away they are, the more ionic the character. Like if your cation comes from here, your anion comes from there, that's definitely a strong ionic compound. If they come from the same side, both nonmetals, then you have a covalent compound. And like any definition, there are exceptions or there are gray areas in between, right? So in between these two, as the elements get closer to one another, they assume more covalent character and less ionic character. But for now, this will hold true, and particularly for naming them, it holds true. So, we're going to start off with naming type 1 compounds. Type 1 binary compounds have a cation, which is named first, and an anion, which is named second. And the cation is monovalent. That means that it only has one possible charge. Right? So it's going to come from either this group, that group, or this group right here. 2 plus 1 plus 2 plus 3. Okay. And the anion will have whatever its charge happens to be. It would come from this group, it'd be -1, so forth. But the key is, for type 1s, the cation has only one possible charge. Okay? The whole scheme of naming compounds, nomenclature, is to name the compound in an unambiguous way. You don't want ambiguity, because if you do have it, then you could write the compound in 2 or more different ways based on the name. You want to be able to write the compound in its formula based on the name, and that's the only way you can write it, based on the name. Right? So, for example, let's go back to this one. That has a plus, minus, so you have 1 and 1 only. So you just say sodium for the cation, and you change the chlorine to chloride. Just change it to IDE. Now we know that if we have this name, the only way you can write it is that symbol and that symbol. This was always +1, always -1. You only need one of them. So that's the only way you can write it. It's unambiguous. Let's take another example. Let's say we have aluminum. Let's say we write aluminum oxide. Bauxite ore. That's what you use, that's what you make aluminum from. Aluminum oxide, is that going to tell us everything we need to know? Yep, because aluminum can only be a +3 charge. And oxide, in this case, is only a 2- charge. Right? So how do we balance those charges? Cross multiply. Take the 2 down here, 3 down there. Check yourself. 3 times 2 minus is 6 minus. 2 times 3 plus is 6 plus. Balanced. Okay? Those are type 1 compounds. So, there are possible cations in there that have multiple charges. So what do you do then? Well, you go to type 2 compounds, in which the cation can have more than one charge. So when you name this compound, you have to specify in the name what's the charge. Right? So any of the other elements, and most of those elements will come from transitions or down here is metals. And when we name the compound, let's take an example. Fe2O3, right? Iron, oxide, but we have to say what's the charge on the iron. So you have to calculate what the charge is. So we know that oxygen is 2- always. So that means it's a 6- total charge, because you have 3 of them. So you have to balance that with 6+ total from the iron. But you got 2 irons, right? So each one is worth a 3+, right? You just put a Roman numeral in there for the 3+. Okay? And with that name, you can write that compound. Right? You say, okay, iron is this, and oxygen's that. We know this one's 2-. That tells us the charge here. So cross over Fe2O3. Okay? That's a type 2 compound. Okay. Now, when you start looking at your periodic table, you're going to find that there are a few, just a handful, of elements in here that only have 1 charge. Silver's one of them. So technically, you could use silver in the type 1 format. But rather than make you know the difference between the two, I just say if it's a transition metal and you write it as, say, silver chloride, you say AgCl, silver chloride without the 1 in there. I'll accept it. Because technically, there's only 1 possible charge, so it's type 1 compound. But since it's come from transition metals, you could say Ag1. You could say silver 1 chloride if you want. Okay. Polyatomics. Let's see, did we get them all done? No. We're going to do polyatomics first. There is, I think in your review document, there's a chart in there with polyatomics. Polyatomics have only 1 possible charge for each of those groups. Okay? So, this example of a polyatomic is OH, hydroxide. And the name for the polyatomic doesn't change. NO3 is nitrate, period. Actually, it's NO3- is the polyatomic nitrate. Sulfate is SO4, 2-. It's always sulfate. So you don't have to change the name. You don't have to say "ide" or anything like that. You just put it in there as is. Let's try one that's not on there. How about this one? Okay. Do you treat this one as a type 1 or a type 2? Type 1. Potassium comes from alkali metals. It's only 1 possible charge. Right? And then you look up PO4. How do you know that that's a polyatomic and not a combination of 3 different elements? Well, one clue is that you have 3 or more elements. One of them is oxygen. If you see an oxygen in there, suspect polyatomics. Go look for it. See if it is. PO4 is a polyatomic. And you'll see from your chart, it has a 3- charge. And that balances 3+ with 1 3- because this behaves as a unit. Okay? So we would say simply potassium phosphate. That's it. Type 1 compound. Now, what if we need, oh, here we go. Let's do it the other direction. Let's say I have magnesium phosphate. Let's write the compound. Okay, magnesium, Mg, phosphate, PO4, This has a 3- charge. This has a what? 2+ charge. And that's all it is. So it's a type 1. So how do we balance the charges? Well, we need to take this 2 over here and this 3 over here. But we can't separate these right here. They have to behave as a group. So you put a parentheses around it. So it's 2 times this 3-, because that 3- belongs to the whole group, not to individual atoms. So 2 times 3-, 3 times 2+ balances. Any questions so far? We're covering a lot of ground.
To work out the formula of an ionic compound, we first select a cation and an anion. Some possible cations are shown here in blue, and some possible anions are shown here in red. Note that the anion might be an oxoanion or other polyatomic anion. Suppose we choose the sodium ion with a +1 ionic charge as the cation and the phosphate ion with a -3 ionic charge as the anion. What is the correct empirical formula for sodium phosphate? Now we can select the number of cations and anions we want to use to build the simplest formula for sodium phosphate. If we select 1 cation and 1 anion, we note that the sum of the charges is -2, so the formula is not constructed properly. We must obtain an overall charge of 0 to have a correct empirical formula. If we add another sodium ion, so that there are 2 cations and 1 anion, we note that the sum of the charges is -1. Therefore, the formula is not constructed properly. We must obtain an overall charge of 0 to have a correct empirical formula. If we add 1 more sodium ion, for a total of 3 sodium ions, we obtain charge balance and a correct empirical formula for sodium phosphate.
There you go. So that, excuse me, that 50 ways to name your compound, that other extra credit, should give you some extra practice also in naming compounds or writing compounds from their names. Okay, last one. Type 3 compounds. These, the first 2 were ionic. The third type is covalent. So these are compounds that are formed between 2 nonmetals. Technically speaking, they don't have charges, right? Because they're covalently bound. Right? So, but we're going to use the binary ionic compound convention to write them. The trick is to figure out which one simulates the cation and which one simulates the anion. Well, if you're working from a name, it's given to you. Right? You're given carbon dioxide. So automatically, this one is considered the cation lookalike and the anion lookalike here. But with type 3 compounds, since you don't have a charge, you have to say how many of each element is in the compound. And this name does. We don't say 1 or mono for this one, because if you got the name, there's always 1. By convention, if the second one is only 1, you will say mono. So you could have, this is carbon dioxide, you could have carbon monoxide. This is the friendlier one. This is the deadly one. Okay. So writing out carbon and oxygen, but you need 2 of them. Okay. That's it. It's all done. This one you need 1 carbon, you need 1 oxygen. That's it. All done. Okay. Now if we go the other direction, let's say, let me think about a compound. A type 3 type compound that would suit. How about Ah. Two nitrogens, three oxygens bound in a single covalent molecule. Right. So, we got nitrogen, but we have two of them. So we say di. That's the Greek prefix for two. And oxygen, we say oxide, but we have three of them. So we say tri. Dinitrogen trioxide. And I think your book or somewhere you should have, let's see. Oh, here we go. The prefixes for all the, for 1 through 10. That's all you're going to need. They go a lot higher than that, but we don't need it. So there's your prefixes. You need to memorize those so that you know what they mean. Mono, di, tri, tetra, penta. Those are pretty easy. Then when you get down here, maybe you might get these two mixed up. Those are your prefixes. And examples, but we're running out of time. Okay. Now, here comes a fly in the ointment. Acids came along before the naming conventions. So we sort of had to bend the naming convention to accommodate them. First of all, what's an acid? How do you know an acid by its formula? It has a hydrogen in it. Starts with a hydrogen. And then something else behind it. So in the first example, if you combine hydrogen and chlorine, if we name this by our previous convention, hydrogen's +1, chlorine's -1, so we would say hydrogen chloride. And that's valid if it's a gas, which it would be, unless you dissolve it in water. If you dissolve it in water, then you're making an acid. Because in water, this hydrogen, actually all of those hydrogens, will transfer to a water molecule. And in that case, if it's, no, it's not liquid. Not liquid. Aqueous. AQ. Means it's an aqueous solution. Then we have to name it with the acid convention. Okay? So, if you have this part of the atom attached to, the molecule attached to a hydrogen, and there's no oxygen, then you start the name with hydro. Always. If there's no oxygen, you say hydro. Then you take the element name and change the ending to ic. Instead of I, you change it to ic. So we say hydrochloric. And then follow with an acid. So dissolved in water, it's hydrochloric acid. That's the first convention. No oxygen. Right? Here's one that's made from a polyatomic, CN, the cyanide ion. Okay, so CN -1 plus hydrogen makes the acid if it's dissolved in water. And that's hydro because there's no oxygen, cyanic. Instead of cyanide ion, it's cyanic acid. Hydrosulfuric acid. The ending here changes just a little bit. Rather than sulfide to sulfic, it just didn't flow. So we'll say sulfuric. So hydrosulfuric is H2S, dissolved in water. Right? If it's not dissolved in water, then you get white sulfur springs. Stinky water, hydrogen sulfide. Okay, what if you do have oxygen? If there is oxygen in the part of the molecule that's not hydrogen, then you don't say hydro. hydro's out, no hydro. What you do is you take the polyatomic, normally what's what it'll be, and if it's NO3, the polyatomic is what? Nitrate. 8s become X. So nitric acid, that's it. What if it was NO2 minus? Right, if you look on your table, you find that NO2 minus is nitrite. So it's the nitrite polyatomic, and ites become us. So that's nitrous acid if it's HNO2. Okay. Then you've got sulfate, 8 becomes X, sulfuric. There's also an SO3. Right? An SO3 is sulfite, so it'd be sulfurous acid. This is acetic acid. Everybody knows acetic acid. Eat a sour pickle. Or you clean up cat pee like I do. You spray it with vinegar, neutralizes it, then you can clean it up. But C2H3O2 in that table would be the acetate ion. So 8 becomes X, it's acetic acid. Okay? And you have to balance the charge, right? So SO4 is 2 minus as a polyatomic, so you need 2 pluses from hydrogen to balance it. Let's see. All right. There's one other trick so that you won't have to memorize so many. There are some groups of polyatomics that make acids, and they're like in a homologous series, we call them. Right? One of them is chlorine combined with oxygen. So I start with this one, ClO3 minus. This is chlorate. Right? So if you add hydrogen to that, it would be chloric acid. Right? If you add an oxygen, then it becomes perchlorate. And then the acid from that is perchloric acid. You take away an oxygen, notice it's still -1 charge. Then you have chlorite, and the acid that forms it from it is chlorous acid. And we go one more. ClO minus is hypochlorite. So it would be hypochlorous acid. So there you have a series of the chlorine, the halogen oxide to make your acids. And you can do that with 2 other halogens. You can put bromine in there. You can put iodine in there. So if you put bromine in there, it'd be perbromate, bromate, bromite, hypobromite. So you can get a lot of these just out of this one series. Once you learn that one, then you can replace these with bromine or iodine. So periodate, iodate, iodite, hypoiodite. Then you can make acids out of them. So that saves you a lot of memory work once you learn one of them. Let's see. We only got a half hour left. Let's see. It's almost the last one. This is the last one. Okay. So just take a couple of minutes. Which of the following compounds is named incorrectly? How about potassium nitrate? That would be a type 1 compound because it doesn't have a Roman numeral in it. So it should say that we have one potassium and one nitrate because this is +1 and that's -1. That's correct. How about TiO2, titanium oxide? Is that Roman numeral correct though? Remember where titanium comes from right here. So it will probably have a Roman numeral. So oxide is 2-. And if we say titanium 2, that means the charge on titanium is 2+, right? So that means one titanium and one oxide will cancel the charge, right? But we've got 1 and 2 here. So that means titanium is actually a 4+ charge, right? So that was wrong. Should be Roman numeral 4. OH is a -1 charge. So if it balances 4 minuses, this one needs to be a +4 charge. And it is. PBr5. All right, so where do they come from? That's the first question you ask. Are they metal, nonmetal, or are they nonmetal, nonmetal? Right, so phosphorus is here, bromine is here. They're both nonmetals. So this is going to be a type 3 compound. So really all you have to do is say 1 phosphorus and 5 bromine. That's true. Calcium, CrO4, is a polyatomic ion. See that oxygen in there? Should say, better look for polyatomics there. Calcium is a +2 because it's an alkaline earth, always. And chromate is a 2- charge, so it only takes 1 of each. It's raining. So the only one that's wrong is that one. Okay. So much for that brain frying lecturing. We'll let that run for a few minutes in case we need to pick up anything from the lab. Let's see. I already handed out your lab, didn't I? I didn't. Did I hand out the safety document? I didn't hand out the safety contract, did I? No, I didn't. Okay. I still need to pick up your and them all in together. So, it is here. Okay, so what I'm looking for here is just a recognition of these rules for safety purposes. Rule number 1 is know what you're doing before you walk in. Know the experiment before you walk in. That's one of the reasons that I had to fill out a lab notebook. And if you do the lab notebook, then you have to think about what you're putting in there, think about the experiment coming. Don't eat, drink, chew gum in the lab. If you have a drink, you can bring it in the lab, but put it up next to the chalkboard on the teaching bench. Okay, so it's away from the experiments. Then you can go access it whenever you get thirsty. That's where I put mine. Everybody knows not to fool around in the lab. Let's see. When you bring your stuff into the lab, be sure and stow it away somewhere where nobody will trip on it, like under the bench would be a good place. Or you could put it up in the front of the lab where your drink is. Let's see, those are the major ones. Always pay attention when you get an experiment or an exercise to do. Pay attention to the safety cautions. There'll be cautionary words in there for safety concerns, and you're going to include those in your written report anyway. When you do a formal report, there'll be a section in there for safety. And we'll talk about that more next time. So go ahead and, if you haven't already started, you notice there are two copies. One's for you and one's for me. So tear the back copy off and give it to me with your, that student number. That's not a telephone number, that's your student ID. So what is it in right here? It starts with an S, doesn't it? And besides that, the name, telephone of your contact, we need to know if you have any medical concerns that we need to watch out for. Like, are you diabetic? Are you epileptic? You know, stuff like that that could put you in danger in the lab if we don't know about it. If you have any serious allergies, you don't have to worry about latex. All our gloves are nitrile. And then next week we'll assign buckets. We have a bucket assigned to each group. It's got some basic glassware and instruments in it. And then the other stuff is either under the lab bench or I'll provide it for each lab. Okay. So where does this go? Right. Throw these away. Until next time. And shut this down. Flash drive out. There you go. All right. Turn this off. There. Turn that on. There you go. Okay. Is your brain humming? How many have had chemistry before? Like in high school? Or? Oh, good. No?
I was a sophomore in high school last time.
Okay. Hopefully it'll come back to you.
I hope so, yeah.
At least in the beginning, the symbols, you relearn the symbols, and then you're off and running. That's most of the memorization. There's a little bit of memorization along the way. Most of it is learning how to solve problems. So let me stop this.